Pleased to announce our first speaker this morning. We've invited Ben to come and give an invited talk all about a topic of his choice, actually. And you're going to be speaking to us about what it takes in OpenCL to support SYCL. So thanks very much, Ben. Over to you.
All right. We made it last day of the conference. So again, I'm Ben. I work for Intel, but this talk is, again, kind of wearing the hat of somebody from the Kronos OpenCL working group, but also a little bit of SYCL, because I touch on a little bit of both. And it's basically, you want to support SYCL, what do you need to do? And especially from the point of view of if you already have an OpenCL driver. And I thought it was actually a really interesting discussion in the panel yesterday. So I think this is that really set up this talk well. So thank you to whoever was asking that question. So a little bit of background just to kind of set the table. Back in the days, SYCL 1.2.1 was developed as a high-level model for OpenCL. Organizationally, the SYCL wasn't its own working group within Kronos. It was a subgroup of the OpenCL working group. And as a result, SYCL and OpenCL were very tightly intertwined. But one of the additions or enhancements in SYCL 2020 was support for additional SYCL backends. And as part of that, SYCL spun off and became its own working group within Kronos. So loosened those ties a little bit. And frankly, this was really great, especially for SYCL. It expanded SYCL beyond the OpenCL ecosystem. And this is why we can have backends for NVIDIA GPUs or AMD GPUs or other devices that don't support OpenCL at all. Despite all of this, OpenCL still really likes SYCL. Tom and I still talk to each other. So, it hasn't been that we've completely separated and gone our own ways. From the point of view of the OpenCL working group, it was less of a breakup and more of, our child has grown up and is ready to go out into the world and do their own amazing things. So definitely want to emphasize that the two groups work very closely together still. And one of the side effects of that is that OpenCL remains a popular implementation choice for SYCL. So even though there are multiple options and people are taking advantage of them, one of the goals of the OpenCL working group is to remain an amazing backend for SYCL. And we work closely with the SYCL working group to make sure that that stays the case. So one of the questions that I get a lot is from companies that basically have an OpenCL implementation, and they want to know, well, what do I need to do if I want to support SYCL? And the good news is you really don't need to do much, at least in theory. You can get by with a fairly basic OpenCL 3.0 implementation. And this is largely because SYCL 1.2.1 targeted OpenCL 1.2. SYCL 2020 made a bunch of changes and enhancements, but SYCL 2020 still tried to serve a large number of devices. And as a result, the hardware requirements to support SYCL 2020 haven't increased too much beyond OpenCL 1.2. In practice, the story is a little bit different. You may need a bit more, especially in the form of optional OpenCL 3.0 features. This is largely because SYCL is based on C++, and the demands of kernels that are written in C++ go beyond some of the demands of kernels that are written in OpenCL-C, especially OpenCL 1.2. So most of the optional requirements are on the device side. You can think of this as being in kernels or things that are generated by the SYCL compiler. You may need a little bit more on the host side for the APIs that are called by the SYCL runtime, but I was going back and trying to think about what gets required by the SYCL runtime, and it's really not much. Mostly if you support a conformant OpenCL 3 implementation, you're going to be all set. A couple of caveats. I am most familiar with the OneAPI data parallel C++ implementation. I think what I'm describing is largely applicable to adaptive CPP also. A lot of these things are theoretical requirements, things that would be required of any SYCL implementation that's built upon OpenCL. So I wouldn't think of this as being tied to any specific implementation. Certainly my hope is that this is applicable to both of the kind of predominant SYCL implementations. Of course, there also may be bugs either in my presentation or my understanding, or even in the SYCL implementations that may require some additional features beyond those that I've described. So caveats, get that out of the way. Let's take a little look at the compilation flow. So basically, this is how Data Parallel C++ compile the SYCL program. And I'm not going to expect everybody to read this, especially the folks in the back. But broadly speaking, there's this piece in the upper right-hand corner where it's taking the SYCL source code and it's finding the device kernels and it's generating LLVMIR out of those SYCL kernels. There's another piece here where it can take those SYCL kernels in LLVMIR and it can generate SPIR-V from them. So SPIR-V again is the Kronos intermediate representation. It's a standard intermediate representation. And then there's another piece here where we can optionally take that SPIR-V and we can generate a target specific binary out of that. And we can take either the SPIR-V form or the target specific binary, and we can basically wrap them up into our SYCL binary that you then shipped with your as part of your application. And we can execute the kernels from either the SPIR-V form or the target specific binary form. So we'll sometimes think of those as the JIT path or the ahead of time compiling path. If I look at adaptive CPP, diagram's a little bit different, but there's largely similar sections of it. There's this piece in the bottom right-hand corner, which is the SPIR-V JIT path. So adaptive CPP can generate SPIR-V as well. And then there's this piece kind of off on the left, which is more of the device-specific binary path. So this is generating a specific binary for a specific device. This would include things like the host or PTX or all the way down to AMD GPU ISA for the AMD GPUs. So broadly speaking, two similar paths. There's a JIT path and there's a ahead of time compile path. So compilation takeaways. For JIT, the path of least resistance is definitely to support SPIR-V and specifically the kernel flavor of SPIR-V, so the compute flavor of SPIR-V. You can see that both the Data Parallel C++ path can generate SPIR-V. The adaptive CPP path can generate SPIR-V. So if you support SPIR-V, you can basically plug right in. OpenCL supports SPIR-V also. So that would definitely be the path of least resistance. If you don't support SPIR-V in your OpenCL implementation yet, there are lots of open source tools that can help. I really do think that it's not as big of an undertaking to support SPIR-V as you might think. With tools like the SPIR-V LLVM translator, if you have an LLVM-based tool chain, you can basically just plug that in and it'll just work. Again, this isn't a strict requirement. There are other options too. You can do something like the ahead of time code path, which would compile to a device binary, which you could then load using a create program with binary type of path. That would work. It might need to do a bit of work in the SYCL implementations to support that. So SPIR-V, strong recommendation, but not a strict requirement. There are some other practical requirements, things that you would need to support in SPIR-V, or just based on the source language. This would be things like the generic address space. So again, SYCL is designed to look like C++ code, and if you look at C++ code, you don't see a lot of address space qualifiers like you would in something in OpenCL. So SYCL pointers aren't qualified with an address space, which basically means you need to support the generic address space. There are paths to do address space inference, but we found that those are effective as an optimization, but less effective as a path for correctness. There are places where address space inference just breaks or it's impossible. So that's brittle, it's error prone. There are probably going to be some SYCL kernels that you aren't going to be able to compile with just address space inference. Support for subgroups, another practical requirement. There are some kind of trivial implementations. You could do something like a subgroup size equals a work group size and then just map between the two. There's also paths for the subgroup size equal to 1. And there was a talk yesterday about some of the pros and cons of implementing a subgroup size equal to 1. There's a lot of code that uses subgroups, so I wouldn't recommend either of those paths. It's a lot better to just support subgroups. But if you really need to kind of get over the hump, supporting subgroups as a trivial implementation is a possibility. And then there's some nice to have like workgroup scans, reduction functions, program scope variables. I think these are things that we could support if an OpenCL implementation didn't support it. But again, it might need some work in the implementations in practice. What is kind of cool is that these aren't like weird esoteric SYCL specific features. Generic address space and subgroups are features that are useful in other contexts as well. So really, if you are developing an OpenCL implementation, these are probably features that you're going to want to have on your roadmap, even in the absence of SYCL. Again, on the host API side, very little is required. If you're OpenCL 3 conformant, pretty much you should be good. But you will notice the asterisks there. And the required is doing a lot of work here. So hold that thought for a moment. But really on the host API side, not a lot of requirements, again, beyond OpenCL 3. So I got a couple of examples here. I went back into my own archives and I found some experiments I'd done on the Raspberry Pi. This was a couple of years ago. It was really early versions of POCL. POCL has gotten a lot better in the last couple of years, and they now support data parallel C++, and probably adaptive CPP as well, much more formally. But this was just an old off-the-shelf POCL. You can see, I think this was based on OpenCL 1.2, and it ran and generated my SYCL Julia set application, which was pretty cool. The hardest part here was honestly compiling LLVM on a Raspberry Pi. This is another example more recently that was an AI startup that had an AI processing unit, and they wanted to support open standards like SYCL. And they wrote this blog post describing how they used the OneAPI construction kit to implement OpenCL for their device. And then they were able to compile and run SYCL programs on their AI processing unit. So that's pretty cool. Really, the takeaway that I would take from here is that there are a lot of open source resources to get started with OpenCL and SYCL. So if you're a new device vendor, you could look at things like the OneAPI construction kit or POCL as ways to get started and to implement OpenCL for your device and then plug into SYCL. Okay, so this kind of comes back to that required piece where the features that I just described are enough to get SYCL working on a device. I think you could probably even pass conformance with those features, but in practice, doing the bare minimum isn't going to let you run a lot of SYCL code that's out there in the wild. Maybe if you have very constrained use cases, maybe you just want to run SYCL on an embedded system and you know exactly what code you're going to run, you're fine with just the minimum. But in practice, there are some optional features in SYCL that you're going to want to support. And I wanted to talk about two of those that the OpenCL working group has been working on that's going to specifically let you run more SYCL applications on an OpenCL device through standard code paths. So the first of those is unified shared memory. It's basically a way of adding support for pointer-based allocations through SYCL. I don't go on Twitter very much, but I did save this one away. A very smart person posted on Twitter about SYCL 2020 USM pointers. And the piece was, USM is used by a lot of applications now, so supporting this will be almost mandatory. In this, it's mentioned that will require OpenCL SVM or the Intel OpenCL USM extensions. I know data parallel C++ doesn't support OpenCL SVM. I don't think adaptive CPP does either.
We have a fallback path, but it's not really tested.
Yeah, so in practice, most of the SYCL implementations that are supporting USM through OpenCL are supporting the Intel extension. And that's primarily because we found that OpenCL SVM, it was a good try at first, but it kind of has the wrong mix of features. So we developed the Intel OpenCL USM extension instead, which we've gotten a lot of mileage out of and is pretty cool, but it'd be really nice to have a standard solution for that instead. So that's what we've been working on. We do have a feature that is in public. Again, this is a change from the way that the OpenCL working group has done business in the past. So this is a Kronos extension. It's a proposal for a standard OpenCL extension that's going to expand SVM to support some of these USM use cases. Really top on our list of extension goals is supporting SYCL 2020 USM. It's not just going to support SYCL 2020 USM, but that's one of the things that we want to consider our minimum viable product. We want to make sure that we're able to support SYCL 2020 USM. We also want to make sure we have things like API consistency with SVM. We want to have compatibility with the Intel extension because we have seen a lot of code that's out there in the wild that's using it. We wanted to build in some extensibility for the future, and then just logistics, nuts and bolts. We wanted to make sure we had really good tests for this feature, and we do have a test plan that's also in the public. And we wanted to make sure we have many implementations because we really do want to think of this as being kind of the new foundation for how to allocate memory and operate on pointers through OpenCL. So I wanted to talk a little bit about how this works. And some of the things that we've added and the way that we've been thinking about unified SVM. And I should mention too, that's a working name. It is subject to change, but I think it's going to stick. So we're going to have a platform query that's going to return an array of SVM capabilities that's supported by the devices in the platform. And because this is an array, we can expand it. So if we find new combinations of SVM capabilities, we've got the mechanism in place to support them. And you can see actually index 4 in this table is some completely new set of SVM capability combinations. So we can have kind of the standard coarse grain, fine grain SVM that you know and maybe love or hate from OpenCL 2, but we also can have the USM and then new combinations. We can also have a device query. And the device query is going to return a parallel array of SVM capabilities that's supported by the specific device in the platform. And this can do two things. It can either return the same set of three things. It can do the same set of capabilities that's supported by the platform. It may also add to some of the platform capabilities. So in this case, index 1 is supporting fine grain SVM with atomics. Maybe there were some other devices in the platform that would only support fine grain SVM. And it can also return 0 if this combination is not supported on the specific device. You can see at index 5, this specific device didn't support system SVM, where if I go back, the platform does support system SVM in index 5. Then we can use this table when we're allocating our SVM. We're basically adding a new allocation API, SVM alloc with properties. And one of the arguments to this allocation function is the SVM type index. So in this case, we're passing the SVM type index of 0. That's going to indicate that we want coarse grain SVM. And we could pass other indices, and that'll get us other types of SVM. We also added this properties. We're not using that in this specific case, but in other types of SVM, this will allow us to pass some additional allocation properties. And it also gives us some extensibility into the future if we need to pass additional information for other types of SVM. We've been adding a couple of additional functions, like an SVM type helper. Basically, you can pass in what your requirements are, and the implementation can pick what it thinks the best type is for those required capabilities. We're adding introspection to query the properties of a pointer. That's something that we thought would be useful and is just missing in the current SVM. We've got some extensibility for SVM-free properties if we need to, and we are going to improve the SVM usability by simplifying indirect access. This is another feature that's used by pretty much every one of the SYCL implementations. Everything else, we're going to use the existing APIs. So you're going to still set your kernel arguments the same way that you would with SVM. If you're copying between SVM allocations, you're going to use the same SVM APIs. So it turns out this extension ends up being fairly small in terms of new APIs and new enums. even though it adds a considerable amount of new functionality. I'm not going to go through this, but there's a ton of links out there. When the slides get posted, you can click through these if you want to learn more. Again, this is an extension that's still in development. So if you have feedback, we'd love to hear it, and you can do so on the pull request. All right, graphs and command buffers. I don't know how much I need to intro this because graphs have been a very popular topic at this conference, but maybe just to put a pretty fine point of it, I got the SYCL llama.cpp last night, and I built it and I ran it on my laptop. And this is a trace of execution through the SYCL llama CPP. And it's actually kind of impressive and scary a little bit. This is a kind of an iteration of the end of llama.cpp, and that big block of color there is representing about 15,000 OpenCL API calls for this particular iteration. And then you can see once those API calls have been made, llama.cpp is waiting for the role to complete, so the block on the top is executing that on the GPU. And what's kind of scary and a little bit unfortunate here is that this just repeats. And I didn't want to put it all on the slide in tiny form, but it just repeats largely over and over and over again. And lest you think that this is a problem with the SYCL implementation, I also built the OpenCL backend for llama.cpp and ran the same model. And the pattern is basically the same. The exact calls are a little bit different, but there's about 11,000 OpenCL API calls. And again, it just repeats. So this is unfortunate for a lot of ways. Basically, there's just too many calls here. You can see that while the OpenCL API calls are being made, the GPU is largely idle. It's also basically keeping my CPU core very active. This is running on an integrated GPU, so when we're taking up CPU cycles, it's actually stealing power from the integrated GPU, so it may be impacting performance in that way. And in this particular case, it's not a problem. Again, this is a laptop, so it's a pretty modest GPU. But if you're on a faster GPU, those 11,000 or 15,000 OpenCL API calls could introduce the host bottleneck, and we just wouldn't be able to feed the GPU fast enough. So we want to fix this. The solution here is basically to do a graph of submissions instead. And a way you can think about that is to replace the individual kernel submissions. So you think of each of these boxes as an OpenCL API call, or in this case, it'd probably be a set of OpenCL API calls to do things like set kernel arguments and then enqueue the kernel. We're going to wrap them all in one big SYCL graph, and then we can submit the SYCL graph as one big chunk instead. The way to think about this from an OpenCL point of view is that we're going to take this SYCL graph and we're going to create an OpenCL command buffer out of it. So from an OpenCL perspective, we're going to take those individual kernels, kerneling queues now, and we're going to put them all into one big command buffer, and we're going to execute the command buffer instead. And we can do that with one OpenCL API call instead of thousands. So the OpenCL working group has been working on a couple of command buffer extensions. We think of these as being basically a family of extensions. So there's a base level extension, and then we've kind of built this so that we can layer a bunch of additional extensions that add additional capabilities on top of that base level extension. These two are extensions that have been provisionally released, which means that we're pretty confident in them, but we do want feedback. And they are subject to change while they're in this provisional status. But these two are pretty far along, and we're hopeful that we can get these to a final state soon. So if you do have feedback for these, we'd like to hear it soon. The base level extension is the command buffer extension, which supports creating and executing what we call static command buffers. So these would be you build one graph and you can't change it, but you can submit it multiple times. And we've also been working on a layered extension that we're calling mutable dispatch that supports modifying some of the kernel dispatches inside of that command buffer. So this would be things like modifying your kernel arguments. If you have like an input to the graph and an output to the graph, you can modify those without rebuilding the entire command buffer. You can also change things like the ND range kernel dimensions inside of the command buffer without rebuilding it. We also have a couple of command buffer features that are a little bit less far along, but these are things that we've been thinking of. And again, these are extensions that are being developed in public. We have kind of a sibling to the command buffer mutable dispatch, which is command buffer mutable memory commands. So this would support modifying the command buffer operands to memory operations. So things like changing the source pointer or the destination pointer to a mem copy, or changing the size of the mem copy. Those would be some examples of things that you could change without rebuilding the entire command buffer. And then we've been have a bunch of issues open to track some additional features that we've been considering. Things like host access to command buffers. So instead of writing to SVM allocations or OpenCL memory objects, it's writing to host memory. Adding support for additional mutability. So maybe you could change the kernel that you're executing, not just the arguments to that kernel. And then things like nested in queue. So submitting a command buffer into another command buffer. Again, all this is happening in public. So if you have feedback, please let us know. In general, we think that our CTS coverage is pretty good. We've been working on the tests kind of as we're finalizing the extensions. Command buffers and the command buffer mutable dispatch both have pretty extensive CTS tests that a lot of vendors are running. And what I think is pretty cool, it took a while, but implementations of these extensions are starting to appear. So you can start to try these out. Again, please provide feedback. We'd love to hear it both for SYCL graph or for command buffers. All right, just to wrap things up. My key takeaway is that if you are interested in supporting SYCL and you are a device vendor, you don't need to implement SYCL. We have two very capable SYCL implementations. You don't need to build your own. Instead, you can plug into those. And supporting OpenCL is a good way of supporting those, plugging into both of those. So if you have OpenCL 3 and a few optional features, chances are you're already pretty close to being able to support SYCL. If you're not quite there yet, there's a lot of open source resources to help out, or even to get started if you're a new device vendor. Things like the OneAPI construction kit or POCL are out there and can get you started with your SYCL support, again, without implementing SYCL. There are two extensions that are needed for many use cases in practice. And these are high priority. These are things that the OpenCL working group is working on. So this would be things like unified SVM, to support SYCL 2020 USM, and command buffers to support SYCL graphs. And again, these extensions are in development, they're in public. We did that specifically so we could get feedback from folks like you. So please give them a look and provide feedback. We all would love to hear about it. And I think that's about it. I think I've got time for a few questions.
Hi, thanks for the talk. I was surprised by the LLAMA dispatch and execution. Why is the execution only starting during CL finish? Shouldn't it be already starting after the very first NQ kernel call?
Yeah, that's a good question. And I noticed that too. I think this is going to be implementation specific. I know I've run this on other GPUs, including other Intel GPUs, and it does start earlier. But there are implementations out there like this one, apparently, that is kind of maximally batching. And it's not starting until the blocking call happens. So.
And what is the delay here? I see it's in milliseconds. It's like 20 microsecond delay. That makes sense. There's a latency for the PCI Express communication, and for that short duration, it's just a coincidence then that it starts during the CL finish, I think.
Yeah, this is a very tight time scale. Yes.
Yeah.
Yep. Good question. Good observation.
You mentioned that it's easy to support SYCL by just running one of the existing implementations on top of your existing OpenCL implementation. But does it also work the other way around? Like, can you make your own single source compute framework in a different language than C++ and use the SYCL backend layers like the JIT and so on as the like device side implementation of that?
I don't know how easy it would be. I guess you could, if you wanted to. It's easier to use some work that some other people have done though, and SYCL is a pretty well thought out standard, and the implementations are pretty good. But yeah, you could always fork it and do something else if you really wanted to.
Yeah, so I guess for this MRCPP, I think maybe it's really implementation dependent. I don't remember we have to wait until CL finish for the GPU to start execute. Maybe,
yeah, I agree.
Yeah.
That was my answer to Moritz also.
Yeah. Also, there's some like because of the framework, the way it works, it's not fully like due to the framework. Sometimes you have to have CPU and GPU interaction even during the one token generation. So there's some overhead there. We are actually working on it.
Sure.
So yeah, that's a comment on this. So I do have a question on this. SYCL, is really C++. Everybody know that the C++ efficiency. I mean, this memory footprint, like a usage, a performance. I mean, it's a kind of like a. I was curious about like Intel. Do you compare against the performance and also like a memory power between SYCL and OpenCL? It's very important for embedded.
Yeah, sure.
mobile.
I mean, in a way, I don't think I'm going to wade into the C versus C++ holy war. But we've seen cases where much like host code that you write for your CPU, you can write good C++ code that performs really well, or you can write really bad C++ code that doesn't perform really well. And the same goes for C. So we have gotten good performance out of SYCL and out of C++.
So for the greedy laziness, you should have come to the tutorial. I make a demo for that. But more seriously, it's a question about the SVM support. I'm curious. So I know right now you have a lot of gap in the SYCL specification for example, mostly multi-devices sharing the same context and all this kind of stuff, like the visibility of the atomic or whatever between multiple devices on the same context and all of these kind of things. The data transfer were possible, implicit or not, or this kind of thing. So does this extension address this kind of thing?
The unified SVM extension? Yeah. Does it support multi? We've been thinking about how to do multi-devices and multi-device contexts. Our focus for now has been on single devices. And that's probably going to be the first version of the extension because that's the most common. Maybe not in your case, but that is the most common as a single device context. But we have been thinking about that. And we've been very careful not to back ourselves into a corner.
Okay, yeah. No, I was just hoping that you already did all the work and we can just copy, but it looked like we need to think together.
Yep.
Okay. Thank you very much, Ben.
Thank you.